Hello everybody, my name is Amine Azide. Welcome back to my YouTube channel. Today we're going to go ahead and start chapter 22. Today in chapter 22 we're going to be talking all about amines. Here we're going to cover the preparation and reactions of amines. When we discuss preparation methods of amines, we're going to cover methods we've discussed before in previous chapters, like preparation of amines from alkyl halides, carboxylic acids, and benzenes. And then we will build on those methods through a few new techniques, such as preparation through substitution and reductive amination. Then we're going to move on to the reactions of amines. This will cover acylation of amines, Hofmann elimination, reactions of amines with nitrous acid, and reactions of aryl diazonomium ions. But first, before we get to all of this, let's remind ourselves of amines and their properties. So here's a quick introduction to amines. Amines are derivatives of ammonia. Remember, ammonia is a nitrogen with 3 hydrogens attached to it. Amines are derivatives of ammonia in the sense that you can get an amine from the replacement of the hydrogens with alkyl or aryl groups. Now, depending on how many of those hydrogens have been replaced, you can assign your amine a classification. If you have replaced 1 hydrogen, then you have a primary amine. 2 hydrogens have been replaced with alkyl or aryl groups, then you have secondary. All 3 hydrogens have been replaced with alkyl or aryl groups, you have a tertiary amine. All right, now, the nitrogen atom of an amine possesses a lone pair, and this represents a region of high electron density. The presence of this lone pair is responsible for most of the reactions exhibited by amines. Specifically, the lone pair can serve as a base or a nucleophile. All right, so this lone pair on the nitrogen can serve as a base where it takes hydrogens, or it can serve as a nucleophile where it attacks electrophiles. Now, in addition, the nitrogen atom of an amine is typically sp3 hybridized, and it takes the shape of a trigonal pyramidal. That makes sense. It has 3 bonds and 1 lone pair. That's the definition of trigonal pyramidal. Fantastic. Now, why not tetrahedral? Well, it does have 4 regions of electron density, but remember, the key point is that one of those is a lone pair, and that is why the geometry of an amine is trigonal pyramidal. Now, as an ending note to our introduction, I present one of the most important things about amines we should not forget, and that is their basic properties. Amines are generally stronger bases than alcohols or ethers, and this point will come up in our later discussion. Now, we want to transition to this topic about how to prepare amines, and we're going to cover a few methods, all with their uses in different synthesis goals. Ultimately, Organic Chemistry 2, if you haven't noticed by now, is introducing you in detail to a lot of functional groups and their preparations and reactions in the hope that you develop a toolbox of reagents and reactions that allow you to answer synthesis pathway problems effectively. And with that being said, this chapter is going to be focusing on amines. And so the first part of that is going to be learning how to prepare amines. So first up is preparing amines from alkyl halides. Amines can be prepared from alkyl halides in a 2-step process in which the alkyl halide is converted to a nitrile. That's the first step, and this is done through SN2 reaction. All right, the reagents needed for this are those of an SN2 reaction. All right, and this is going to be followed by our favorite reducing reagent, and that's lithium aluminum hydroxide. So we can prepare amines from alkyl halides by first taking our alkyl halide, converting it to a nitrile through using cyanide, sodium cyanide, through an SN2 reaction, and then taking this nitrile, further reducing it to get that amine. Next, we can prepare amines from carboxylic acid. The carboxylic acid is first converted into an amide, all right, which is then reduced to give an amine. And we've seen reagents that do this. We just recently talked about the reagent needed to convert from carboxylic acid to an amide, and that's this reagent right here. And then again, we treat with our favorite reducing reagent, lithium aluminum hydroxide, to get our final amine product. Third, we can prepare amines from benzene. We can take a benzene ring and introduce a nitro group. We know how to do this. We've covered this. These are the reagents we need. Nitric acid and sulfuric acid. We add a nitro group to our benzene. All right, so then what we can do is convert to an amine group to get an aniline. This first step involves nitration of the aromatic ring, and the second step involves reduction of the nitro group. So several reagents can actually be used to accomplish this reduction, including hydrogenation in the presence of a catalyst or reduction with either iron, zinc, tin, chloride in the presence of aqueous acid. The latter method is more mild approach that is used when other functional groups are present that would also be susceptible to hydrogenation. Before moving on to more preparation methods, right? We've covered 3 now: preparing amines from alkyl halides, carboxylic acids, and preparing aniline and its derivatives from benzene. So we know how to add a nitro group to our benzene, and then taking that nitro group, getting that amine group on there through 2 methods. Now that we have all this, and most of this is friendly reminder, just to solidify this knowledge, let's do a few practice problems. Draw the structure of an alkyl halide or a carboxylic acid that might serve as a precursor in the preparation of each of the following amines. So looking at A, all right, how can we start from, say, an alkyl halide and progress to get this amine? Well, we actually just saw something very similar to that. We can start with an alkyl halide, something like this. Then we can treat it with cyanide through an SN2 reaction, right? And what we get now is SN. And then we could further reduce this to get our final product, and we can use our favorite reducing agent, which is lithium aluminum hydride with water. All right, and that will give us our final amine, and that will get us our product. Fantastic. Now you can do this another way as well. You can do this with carboxylic acid. That's absolutely correct. You could start with a carboxylic acid, convert it to, convert that alcohol group in your carboxylic acid to chlorine, then convert it to an amide, and then reduce it back. We've seen how to do this. This is just one way, using an alkyl halide. You could have done it with a carboxylic acid. All right, now let's do B. All right, we are starting with this, and we want to start with something, maybe a carboxylic acid this time. You can do this, each one of these problems you can do either with an alkyl halide or carboxylic acid. You should try to do both just to make sure you are understanding fully. I'm just going to use one or the other and let you try to explore the other option. We're going to start with the carboxylic acid since we did alkyl halide in A. Let's do carboxylic acid for B. So here's our carboxylic acid. What we can do is take this carboxylic acid and convert it to an acid chloride. All right, add a chloride here. We know exactly how to do this. SOCl2. Then we can now take this and convert it to an amide. All right, all we use is excess amine for that. and we can get an amide. So this will look like something like this. Ooh, that's not enough space. We can get something that looks like this. NH2. Perfect. Now, as a final step, we can take this, reduce it using our favorite reducing agent, excess lithium aluminum hydride, with water. And what we get finally is our desired product, our amine that we were asked for. All right, fantastic. I'll let you attempt C and let me know if you have any questions. But with that, we want to continue our preparation methods. And now what we want to do is we can prepare amines through substitution reactions. And actually, there are several ways to approach this. One procedure is alkylation of ammonia. Specifically, ammonia is a very good nucleophile, and it will readily undergo alkylation when treated with an alkyl halide. All right. So when you take ammonia, treat it with some alkyl halide, all right, you can start to alkylate your ammonia, hence alkylation of ammonia. You can start adding some sort of alkyl group like a methyl or an ethyl or whatever else to it. You could actually, alkylation of ammonia. So now let's actually break this down. It's pretty straightforward, right? You start with ammonia, treat it with the alkyl halide that you require, right? So halogen attached to whatever alkyl group you want to attach. So whether that be methyl or ethyl or even like a butyl or a phenyl, whatever, and you can alkylate your ammonia this way. This reaction is going to proceed through an SN2 process that's actually followed, this last step, it's followed by deprotonation to give your primary amine. Now, as the primary amine is formed, here's the catch. It can undergo further alkylation to produce secondary amine and then even further to produce tertiary amine. So that's kind of the catch for alkylation of ammonia. Now, finally, the tertiary amine can undergo alkylation one more time to produce a quaternary ammonium salt. An important consequence of this process, as you see, that monoalkylation is very difficult to achieve through this technique. So you really want to keep this in mind when you do synthesis problems. If you're asked for a certain desirable product, and you think that midway through the synthesis pathways, you can employ alkylation of ammonia and expect one specific product, well, you need to remember that monoalkylation is difficult. You're not probably going to get a primary amine if that is what you're desiring. You're probably going to get a secondary or tertiary because further alkylation occurs. All right, so keep that in mind. That after that primary amine, you can get to secondary amine. You just do alkylation again, tertiary amine, and even all the way to the end to get that ammonium. All right, fantastic. Now, next up is azide synthesis. The azide synthesis is a better method for preparing primary amines than alkylation of ammonia. Why? Because it avoids that formation of secondary and tertiary amines. This method involves treating an alkyl halide with sodium azide that's followed by a reducing agent. All right, so let's look at this. Followed by reduction. Reducing agent reduction. Let's take a look at the mechanism for this because it's important since it's the better method for producing primary amines without further alkylation like we saw with alkylation of ammonia. We should understand why it works without further alkylation. So in the first step of this mechanism, the azide ion is going to function as a nucleophile. And what it's going to do is attack the alkyl halide in an SN2 process, producing an alkyl azide. So we could see this right here. Here's the azide ion. It's going to function as a nucleophile. Here's our alkyl halide. It's going to attack that. And what it's going to do is, when it attacks that, it's going to expel the halide as a leaving group. So goodbye halide group. So what we get now is this alkyl azide. That's what it's called, alkyl azide. Fantastic. Now this alkyl azide is then reduced using lithium aluminum hydride, our favorite reducing agent. All right, so what lithium aluminum hydride does is it transfers a hydride ion to this alkyl azide. And when performing this procedure, special precautions are usually observed because, believe it or not, alkyl azides can be explosive, and what they can do is they can liberate some nitrogen gas. All right. Now, after your lithium aluminum hydride step, nitrogen gas is expelled as a leaving group, giving an amide ion. And this amide ion is protonated finally to give your final product, your primary amine. And this is the mechanism for azide synthesis. This can stop after the first alkylation. And so this is going to be really useful when we get to our synthesis problems. Now we're going to follow up with Gabriel synthesis. This is a method for preparing amines also while avoiding formation of secondary and tertiary amines. The key reagent here is potassium phthalimide, which is prepared by treating phthalimide with potassium hydroxide. This reaction, sorry, I thought it scrolled, but it froze for a second. This reaction is gonna proceed through an SN2 process, so it works best with primary alkyl halides. Again, this is the same reason our azide synthesis was really great at producing primary amines without going further, is because of that SN2 process, and that works best with primary alkyl halides. Now, it can be performed with secondary alkyl halides in many cases, but tertiary alkydes are a no-no. Now, acid catalyzed or base catalyzed hydrolysis is then performed to release the amine. Acidic conditions are usually a little more common than basic conditions, but all in all, you get the same end goal. And the Gabriel synthesis is just another method for preparing primary amines while avoiding forming secondary or tertiary amines. And this is just a breakdown of how that works. Now, let's do a few practice problems on Gabriel synthesis just to solidify our understanding here. Using Gabriel synthesis, show how you would make each of the following compounds. So this is our end goal, and we want to make sure that this is what we're getting. Taking advantage of our Gabriel synthesis, which, by the way, is another method for doing this, with the key reagent being potassium phthalimide and this reagent right here, or this molecule right here. So if our goal is to form this amine as our product, all right, we're going to go ahead, we're going to get started with something that looks like this. That's not very good. There we go. With our double bonds right here. All right, we're gonna go ahead and start here. Now, we can treat this with our potassium phthalimide. All right, and also with what we're trying to obtain as an amine at the end, but as a alkyl halide, right? And then finally converting that to the amine that we want. All right, so let's break this down. You're starting off with this molecule. We saw something like this when we were looking at Gabriel synthesis. You start with this molecule, you treat it with potassium phthalimide, and what you get is this nitrogen with a negative charge because the hydrogen was taken and its lone pairs were left behind. So now this nitrogen has a negative charge, right? And you can treat it with some alkyl halide and it will attach to it. All right. Now, ultimately, this can be treated further so that you can release your desired amide. All right. And how this works is whatever alkyl halide you treat it with, say RBr, right? This R group gets attached here minus the halogen that you've attached to it. And then you can further treat it with hydrazine or some aqueous acid, hence what we were talking about, that you can further treat it with acid or base catalyzed reagents to then separate the two and ultimately obtain the R group attached to an amine. So that's what we're doing here. We're starting off with this molecule. All right, we're treating it with the potassium thalmide and then an alkyl halide. What we get as an intermediate step here then is something that looks like this. Fantastic. Now what we can do is actually take this one further step, all right, through acid or base catalyzed hydrolysis to then release the amine. And so you can use something like, and I wrote excess this, but you might want to use something like hydrazine. And this is actually going to look something like H2 nitrogen H2. All right, that's what your hydrazine looks like. Something like this. With the hydrogens on it. Fantastic. All right, so you could treat it with hydrazine, and what that will do is it'll break off the portion that you want, and that is how you get this product of the Gabriel synthesis. It's kind of hard to see that play out here, which is why I really wanted to do this practice problem. Now we can go back to Gabriel synthesis, and we can reiterate that this, yes, is another method for preparing primary amines. It does it by using this starting reagent, treating it with potassium thalmate, all right, and then treating it with some alkyl halide and attaching an alkyl group to this molecule so that you get something like this. Then through an acid catalyzed or base catalyzed workup, you can release the amine that you want. All right, and so that's how it works. That's exactly what we did here. We took this molecule, treated it with potassium hydroxide, to get our thalmate that we want, treated it with an alkyl halide that attached to it, and then we can work it up with hydrazine to then, right, acid or base catalyzed, whatever you want, and you obtain the portion that you desire, ultimately H2. And that's how you do that. All right, so I'll let you attempt B, C, and D. Let me know what you get, and if you want help, feel free to reach out to me. Now, last but not least, let's discuss our final amine preparation method. Preparation of amines via reductive amination. Recall that ketones or aldehydes can be converted into amines. And let me write that up because I don't want you to confuse amines and amines, and I have a bad time pronouncing this. Ketones or aldehydes can be converted to amines when treated with ammonia in acidic conditions. If the reaction is carried out in the presence of a reducing agent, such as H2, molecular hydrogen, then the amine is reduced as soon as it's formed, and what you get is an amine. And this process is called reductive amination. So remember, you could take a ketone and convert it to an amine, all right, using some acid and NH3. Now you can take this amine, and if you treat it with molecular hydrogen and some sort of catalyst like platinum, it can be automatically converted to an amine. Fantastic. So many other reagents actually are also frequently used instead of hydrogenation. One common reducing reagent for this kind of process is sodium cyanoborohydride. I believe that's how you pronounce it, but I can write it down for you. It's right here. Actually, that's awesome. You can use this as a reducing agent for this particular reaction. It's similar in structure to sodium borohydride, but a cyano group has replaced one of the hydrogen atoms. Now, this process can't be achieved with just sodium borohydride, which would simply just reduce the ketone before it's converted. But with sodium cyanoborohydride, you can actually do this because it does not react with the ketones, but it'll just reduce your amine. And this process enables the conversion of a ketone and aldehyde into an amine in one reaction flask. So the identity of the nucleophile pretty much also, by the way, can be changed along with using sodium cyanoborohydride to prepare not just primary but secondary and tertiary amines. So conceptually, you can take a ketone, all right, and through the same process you would convert it to an amine, but with the addition of same molecular hydrogen, it'll automatically convert to an amine, and you can get amines now from ketones or aldehydes. You could do the same thing instead of molecular hydrogen with sodium cyanoborohydride. And the nice thing with sodium cyanoborohydride is you can treat it with a primary amine, secondary or tertiary, and get specific outcomes that you want. It's not just restrictive to the creation of primary amines, but you can actually use this technique to produce secondary amines and tertiary amines. And so that's going to be really important for synthesis later down the line. Now, let's do a few practice problems to ensure that we understand this technique. So this says, show 2 different ways of preparing each of the following compounds through reductive amination. I'm going to show you one, and I'll leave the other way for you to figure out. So for A, all right, show 2 different ways of preparing each of the following compounds through reductive amination. Fantastic. Now, one way we can do this is we can start off with, say, a ketone or aldehyde. Let's start with an aldehyde. All right, we just learned we can take aldehydes or ketones and through reductive amination create primary, secondary, or tertiary amines. So let's take advantage of this. If we start with an aldehyde and we ultimately want something that looks like this, right? Still 5-membered ring, but instead of this aldehyde, it's NH, and then it has a benzene at the end of it. So this is what we're trying to get. All right, so how are we going to take this aldehyde and ultimately convert it to this molecule right here? Well, what we can do is treat this with sodium cyanoborohydride, all right, and treat it with the portion of the molecule that we want to add. So if we're starting off with this aldehyde that has a 5-membered ring, all right, and it's an aldehyde, what we want to be adding to this molecule is this latter portion of the molecule, right? Because we're starting off with an aldehyde that has a 5-membered ring. So that means we want to add the latter half of the molecule to it. So what we're going to be treating it with is sodium borohydride, and what we want this aldehyde portion to be converted to, and that looks like a 6-membered ring and our NH2. What happens here, just like we've seen here, right? If you take an aldehyde or ketone, you treat it with sodium borohydride and the amine group that you want, you can take this carbonyl group and ultimately change it to your amine group plus whatever alkyl group is attached to that. All right, so we can do that. Now, what they mean by show 2 different ways is you can actually start with an aldehyde that it has a 6-membered ring, and you can do the same procedure. You can do the same procedure to get this final product, except, yeah, you're still treating it with sodium cyanoborohydride, but this time the nitro group you're treating it with is going to be the other portion of the group. So if you're starting with an aldehyde that looks like this, you want to add through reductive amination this other portion so it looks like this at the end. So that means you want to treat it with a 5-membered ring amine. All right, and so if you treat these two things together, you get this, or you could treat these two things together and get this. Either way, you are still obtaining the final product by taking advantage of the using an aldehyde, all right, converting it to an amine using reductive amination. Fantastic. Go ahead and attempt the other two and let me know if you have any questions or if you want me to go back and work through them. I'm more than happy to do that. So far, we've explored a variety of methods for preparing primary amines. Each of these methods utilize a different source of nitrogen atoms. The Gabriel synthesis uses potassium tholuamide as the source of nitrogen. The Azide synthesis uses sodium azide as the source of nitrogen. And reductive amination uses ammonia as the source of nitrogen. When preparing primary amine, the available starting material dictates which one of these three methods will be chosen. All right, and with certain methods, you can actually work with creating more than just primary amines, but secondary and tertiary amines are also possible, as we have seen. So in order to create a primary amine, you can use either one of these syntheses, Gabriel, Azide, or reductive amination. With reductive amination, you can also produce secondary or tertiary amines as well. They are not limited to just primary amines. And you can see that here. You can use all of these techniques to get to a primary amine, and then through further reductive amination, get secondary, tertiary, or even quaternary amines. So these are all really good synthesis techniques to keep in mind, especially now as we will do a synthesis problem before we end our session for today. All right, so we're going to go ahead. We're going to look at this first practice problem. Using ammonia as your source of nitrogen, show the reagents you would use to prepare each of the following amines. We're just going to go ahead and do A. All right, looking at A. All right, here's our amine. Okay, fantastic. The amine, it's secondary, so that's an important thing to note. We have a secondary amine. All right, that means it bears two alkyl groups. All right, we're starting. The problem says that the source of nitrogen is ammonia. All right, which dictates that each group is going to be installed through reductive amination. All right, so that makes sense, right? We have to start with ammonia. All right, but we want to get this secondary amine. So we can use any of these techniques to get to a primary amine, but then to elaborate further on it, we would have to use reductive amination. All right, fantastic. That's super good to know because now we can tailor our synthesis using that strategy. What we can do now is either use some technique to get ammonia into a primary amine and then do reductive amination, or we can just work with reductive amination from the beginning. Both techniques are allowed, and there's actually methods to use either techniques to get to the correct answer. I'm going to show you what I think is probably easiest, and that's just to use reductive amination to get this secondary amine. All right, so what we can do is take this molecule right here, and what we're going to do is we're going to break it at the two places right here. All right, it's a secondary amine. We're going to break it there and there. What this means is we can start off with this portion of the molecule as something. All right, and we have to work with ammonia, NH3 somehow in some form. All right, and then this latter portion of the molecule, which could be something. All right, these could be aldehydes that we use in reductive amination, and actually we're going to use that as inspiration to do our first conversion of ammonia to primary amine. All right, to primary amine. How are we going to do that? We're going to take this first portion. You could take either or. I'm going to just take this bigger portion. I'm going to make this a aldehyde. All right, we're going to start off with an aldehyde and ammonia. Okay, so we still have our ammonia that we're working with and we're starting off with. But in addition to our ammonia, we're going to treat it with this aldehyde. This aldehyde, ammonia, and then some of our sodium cyanoborohydride is going to do something very cool. And that is going to take our aldehyde group, this carbonyl and hydrogen, convert it to a primary amine. So let's write sodium cyanoborohydride. So we've started with what the question told us. That's this ammonia. All right. In addition to the ammonia, we're starting off with this aldehyde. We're going to treat this ammonia with this aldehyde and sodium cyanoborohydride. What is this going to do? It's going to take this portion of our molecule and convert it to an amine. So what we're going to get as a consequence of that now is something that looks like this. NH2. And then, of course, these two groups right here. Fantastic. Now this will be easy. We have our primary amine. We want to get it to that secondary amine. We can do reductive amination again. And all we need is acid. And again, our sodium cyanoborohydride. All right. What this is going to do is it's going to... Oh, and something else. Well, what is the other group that we need to add to this? It's 2 carbons. All right, so we're going to treat it along with this with a 2-carbon aldehyde. So 2-carbon aldehyde. Fantastic. This is our 2-carbon aldehyde. What is this going to do now? Well, the sodium cyanoborohydride is going to add to this primary amine these 2 carbons right here. All right, so to this 2-carbon aldehyde, we're going to be adding this. That is how reductive amination works. And as a final product, what we get is what we desire. And that's how reductive amination can work to do this process. And that's how you can use ammonia as your source of nitrogen and work it up to get either a primary, secondary, or tertiary amine. In this case, it was a secondary amine. I'll let you work on B and C. Let me know if you have any questions at all. This will be the end of this session. Next session, we'll finish all of chapter 22. Let me know if you have any questions. But other than that, good luck, happy studying, and have a fantastic day.